Welcome back. So previously we discussed exponential functions on the study guide memorize sheet, and we just kind of walked through what the formulas did and like a couple of really basic examples in here. Not listed here, well at least not in this section, but remember that the base function for exponentials is f of x equals ab to the x. That's where these are all kind of derived from. But we have exponential growth and decay, which is this formula here. We have compound interest, and we have continuous exponential. So let's take a look at some examples of these. So if I have, put that notation in there, A is our initial value. 1 brings our principal balance back in. R is the rate in decimals, and X is the number of iterations, the number of times we repeat this cycle. So if we had a problem where, let's say somebody had a car and the current valuation is $3,000. They think it's going to depreciate in value, so decay, at 3% a year. And they want to know the value after 10 years. So let's make this y, actually write this out, y after 10 years is equal to 3,000, 1 minus 0.03, remember to make it into a decimal, to the 10. And we can throw that into a calculator to find that it is 2212.27, or actually it's a rounded value, so let's round that value. Obviously we're dealing with dollars, so I mean this is the value that would make sense. One thing I wanted to say you should pay attention to is, do they want the value after 10 years, or do they want the change in value after 10 years? So be careful to how the question is phrased. I phrased it, obviously, what would the value be after 10 years, not what would the change in value be. But be aware that the practice may play around with that wording, and you need to pay attention. So if we go on to compound interest then, so this is essentially the same formula. What we're doing is we're accounting for compounding over a certain interval of time that may be different than our time frame that we're actually looking at for x. So in this case we have a $1,000 initial investment, and they are compounding interest at 4% every 6 months. So R is 0.04, and we determine our N via this right here, every 6 months. So if they want to compound every 6 months and X is in years, then we are going to have N equaling 2, right? We compound twice in the year. And then we have X. And the question they're asking is, how long till 2A? So how long till we double our initial investment? $1,000 doubled would be $2,000. So first of all, let's see, we're trying to isolate X, so let's get rid of this 1,000. We get 2 is equal to, in the parentheses, 0.04 divided by 2 is 0.02, so 1 plus 0.02 is 1.02 to the 2x. Now, recall that when we have this type of situation, to pull it back down, we need to use rules of logarithms. So we're going to end up taking the log of both sides. What that ends up looking like, So if we took the log m n o, remember that in this situation we can pull the o to the front. So we take the log of both sides then, or the natural log of both sides, we can pull the 2x to the front. ln of 2 is equal to 2x ln 1.02. And then we just divide to get x by itself. ln 1.02. And we can throw that into a calculator. To receive 17.5. And again, this is not exact. We have decimals. So at this point we got to ask, or we have to ask, because they're wanting to know how long. I didn't specify at the beginning, but let's specify it now that we want in years. Answer in years. So if that happens, how do we round this? Well, we needed to double the value. At 17, the value is beneath 2000, and at 18, it's above. So when you get problems like this, if it's unclear to you, round to what makes sense, right? So if we need to double our value, it's better to go a little bit over than to go a little under when we're looking at your return on an investment. So in that case, we would round to 18. So let's go onwards to continuous exponential growth. So we have a continuous growth rate of 0.04 per hour. So when you're looking at continuous growth rate, I can't drive this home enough. We're not talking about when we're normally considering rates where we have, steps, miles per hour, or or literally looking at like stairs. You walk up one stair, you go to that height, walk up another stair, go to that height, walk up another stair, go to that height. It's a straight line, right? Continuous. So continuous growth rate of 0.04 in hours. We have a bacteria population, and the initial value is 200. What is our value going to be at 7 hours? So y at 7 is equal to the initial value times E, Euler's constant. Again, it's about 2.72. Use your calculator key. Don't round. To the K, which is 0.04, times X, which in this case is 7. And we can plug that in and see what we get. We get, again, roughly 264.63. So again, with the concept of rounding, if they asked you for a population and you have to, it's like one of the questions on the Praxis where you have to enter in a number into the box and wants a whole number, how do we round this? Well, reasonably, if they're talking about bacteria, let's just assume that a 0.63 of a bacteria can't survive. So if we think about it that way, then our answer would be 264. So in the last problem, it made sense to round up. In this problem, it makes sense to round down. So yeah, if you're confused at all, go by common sense. And that should do it for this video.